particles with matter. And firstly, I would like to remind you, remember the matrix that we divide all particles into two categories: charged particles and uncharged particles. Charged particles are electrons, light particles, and heavy particles like protons and ions. Also, we touched uncharged particle and talked about interaction of gamma rays with matter. Remember three processes: photo effect, Compton scattering, and reduction. Now we have to talk about the last particles, neutral particles, which are called neutrons. And as you remember from the last lecture, all these particles interact differently with matter due to its nature. And today, we're going to finish the interaction of different particles with matter and go to devices which detect this radiation. These are called radiation detectors. Neutrons, as you remember, have zero particle charge. That's the name. And the main difference between neutrons and other particles that their cross-section or the probability to interact with matter strongly depends on the energy of the neutron. That is why it's very important to divide neutrons to different categories depending on their energy. And as you remember, neutrons are neutron particles, and in order to analyze the matter, they do it indirectly. They should create the secondary particles. And here, this, if you want, a typical fate of neutrons, all neutrons originally are born like fast neutrons. Yeah? We have to somehow characterize our neutrons, and we characterize them by energy. And the simplest characterization is divide them into two categories: fast neutrons and slow neutrons. From the detection of the neutrons, that's the route and the most simple way to distinguish between neutrons. And there is some limit, which is called cadmium cutoff, which is really a rough estimation that shows that all neutrons which have the energy more than half of electron volt are considered fast neutrons, which are lower, they're considered slower neutrons. But actually, it's one of the simplest characterizations. Actually, there are more neutron categories, and I will show them on the next slide. So, in order to understand, all neutrons are born fast. Here it's neutron. If it's fast, it has enough energy, for example, as 1 MeV of its kinetic energy. And then neutron starts interacting with matter surrounding it. And the first object that it is, it's a nucleus of the surrounding material. And neutron can scatter all the of this nucleus and start moving forward. Then finds the second nucleus, schedules, transfer some energy to the nucleus, one more time, and finally, it should be captured. The most probable way to be captured, then the nuclear energy is at 25 MeV nearly electric volts of energy. And these neutrons are called thermal neutrons, and they have very high probability of being captured. And in this case, neutrons, neutron dissipates when it's captured. So, usually there are two ways of the neutron to take some power. It can be scattered or absorbed. Thank you very much. So now more precise division of neutrons by energy. You can see here in this table, we have first of all neutrons with energy less than this value, 25 MeV, which neutrons are called cold neutrons, and they are pretty small. Thermal neutrons, why we call them thermal, because they are thermalized with the surrounding materials, have the same energy and temperature that the atoms or molecules surrounding it. There is also the thermal neutrons, cadmium neutrons, slow neutrons, like this region. There are also resonance neutrons, which have energy in this region from about 10 MeV to 300 MeV, and intermediate neutrons, and of course, neutrons with energy like this, from 1 MeV to 20 MeV, and relativistic neutrons with energy more than 20 MeV. But this, frankly speaking, quite rough categorization of neutrons, because in some literature you can find different energies, different names of these neutrons, but basically I use this table. I'm talking about behavior neutrons and how they interact with matter. You can see a typical graph in here. You can see bars. That's the unit of neutron cross section and neutron energy. You can see that the cross section has decreasing in this energy region, then it's wide as a horizontal part, and then has some peaks in spectrum for some elements. And you can see here different elements: water, iron, and aluminum. And here, this line shows the thermal energy threshold, 25 MeV of energy. And here you can see decrease. This inversely proportional to the velocity of the neutron, and these peaks are called resonances. A sharp decrease in or increase in cross section due to in some energy regions. This thing can be very useful in some applications. You can see the values for these materials, and I just showed in this graph show that the cross section for different elements differs significantly. There are several types of interaction of neutrons with matter. As I said, it can be scattering or absorption. If we are talking about scattering, there are two ways to scatter. That's elastic scattering, like the billiard ball effect. We have, if we play billiard, you will hit one ball and then pause and transfer some energy to the other. And this process, the kinetic energy of this interaction is resolved, and you can have that you receive 0.4 MeV. The whole energy of the neutron is divided between the energy of scattered neutron and the nucleus. Why that's important? Because when we talk about elastic scattering, it's very important to slow neutrons. And we use materials which are called moderators, such as water, paraffin, plastic, and graphite, for example, that have light elements which can sufficiently slow neutrons during interactions. Why we use light materials? If you look at this picture, that's a simplified version of interaction of recoil of elastic scattering. We have any kind of neutron. Here's a nucleus, which is actually at rest. It's called the target nucleus. We have, of course, a scattered neutron after the interaction, and the nucleus gets some energy, and it's called the nucleus recoil. And the most amount of energy is transferred to the nucleus. You can see here that just list some formulas in order to just show you a simple question showing that the energy of nuclear recoil is equal to this equation, where R the atomic mass and theta is the angle of scattering energy of the coil, and EM is the energy of the original energy of the entire unit. And if you look at this formula, you can see that the energy of the recoil going to the maximum, the cosine is equal to 1. Yeah, and that happens when you have a hadron collision, when the angle is actually 0. In this case, if you equal this to 0, you can see that the maximum energy can be transferred using this equation. And here, some examples of elements, which most common moderators here: hydrogen, helium, carbon. As I said, here you can see the ratio of energy transferred to the nuclear coil. So the second process is called inelastic scattering. In this case, not all the energy is divided between not all kinetic energy divided between the scattered neutron side of nucleus, because we have some energy that goes to the excitation. And we have, for example, the same neutron with one MeV. We have a scattering neutron with energy 4.5 MeV, and we have the energy of the nucleus about 0.3 MeV. And the 4.1 MeV of energy went to the excitation of this unit. Basically, inelastic scattering is characteristic for elements which have high Z number and for high energy. Here you can see the example of the cross section, the energy movement, the cross section, and you can see that this is a threshold process. For example, for ferrite 56, we have this area, this cross section, in the last scattering. This process is a threshold process because we have a minimum amount of energy which is required to excite the target molecule. Now we can talk about some processes which are happening in neutrons absorption mechanism. We talked about scattering, now we're talking about absorption. Why absorption is so important? Because in order to detect a neutron, we have to transfer its energy to other particle, specifically charged particle, which can ionize the matter. So remember, only charged particle can directly ionize the matter. And here's some examples of how neutrons are absorbed and give rise to new particles, specifically charged particles. Here you can see most common reactions which are used to detect neutrons. The first one is a neutron interacts with helium-3, and you get a tritium and proton reaction. This here you can see the cross section. This is actually cross section for thermal neutrons. One more reaction, it's a threshold reaction. You can see graphs showing how it cross section depends on the energy of the particle. And the second type of reaction is then alphas appear. Alphas also charged particles and can directly ionize matter. That is why we use lithium-6 reactions and boron-10 reactions. Here we can get also tritium and helium, which is alpha particle, or here lithium decided and helium boron alpha particle. Here cross section for thermal neutrons. So let's move further. Some more reactions where we can get other particles that can, for example, ionize, or just a reaction where neutrons are absorbed. Here, this is a reaction which is called neutron capture. In this reaction, as we can understand from the name of this process, neutron is captured by some atom. Basically, this is reaction for hydrogen. Yeah, we have, why this reaction is very important, because it neutrons interact with water. They give rise to this 2.10 MeV gamma rays. Cross section is pretty low, for example, compared to this reaction. where cadmium-113 is used, which is very important for and one of the most common elements used to capture the Newton, because the cross section is very high, even by Newton standards, 20,000. I think we talk about gadolinium, it's even more. One of the most frequently used Newton capture materials. One more example how we can make and how we make make disappear our neutron. This is called very well-known reaction, which is called fission reaction, which is used in nuclear reactors. And in this process, neutron is captured, yes, and we have some heavy fragments like this, elements with masses here and here, and on average about from 2 to 4 newtons. These materials, which tend to capture neutrons and produce more neutrons and fission fragments, are called Zal materials. And the right example of this cyanide isotopes, which are uranium, uranium 5, plutonium, and so on. In this reaction, all kinetic energy, almost all kinetic energy is released in the form of fission fragments, about 160 MeV, and fission neutrons get 6 MeV, gammas 6 MeV, because we have excited, sometimes excited fission fragments, which give rise to gamma rays. Beta decays also to the excitation of the fission fragments, and of course about 10 MeV of energy goes to the neutrinos, which actually is taking energy from this reaction. Why we are so okay, just some exotic reaction can be used also when we have, for example, 2 neutrons. These neutron 2 neutron reactions, but these are reactions quite exotic. Not so many elements, they can produce 2 neutrons, and basically these reactions have a threshold of several MeV. I just get to show the scope of this reaction. And if we summarize all our possibilities of neutrons, yeah, we have neutron can scatter or get absorbed. There are many ways of doing this. That's the same thing like for gamma rays. You have a cross section, a total cross section, which really is the sum of all cross sections and possible ways of interaction. For example, there are 2 scattering cross sections, inelastic scattering. We have absorption cross section, capture, fission cross section, fusion cross section, and the total, or even nuclide, is the sum of all individual cross sections for that nuclide. You have to summarize for scattering, elastic or inelastic scattering, and so on. To summarize all cross sections, in this case, we will get the total cross section. And the total cross section is very important in the same way for gamma rays. Of course, we have and get the microscopic cross section, which is similar actually to the linear attenuation coefficient for gamma rays. And you can see that it's also in the unit source. In gross centimeters, and for some and in the actually the concentration atoms expressed in and the microscopic cross section actually is the probability per unit path length that neutron is removed from the beam. You have a narrow beam of neutrons. There, some of them are scheduled, some of them are absorbed. So you have the same exponential equation. So I think we covered all ways how neutrons and how particles interact with matter, and we can go to radiation detectors. Just to remind you what we can how we detect particles. We have some material, we have an ionizing particle. And in order to detect this particle, the only way to do it is to calculate the energy losses of the particle in the detector. And when the particle passes through the matter, specifically charged particle, its energy losses can be divided into several categories, but the main category is ionization, and we have ion and electron pairs on the track, along the track of passing through the matter particle, and excitation, when you have then some atoms usually their interaction with the particle with the atom can go to the excited state. And the third channel, which is used to where energy can be lost as well, is heat. But actually, heat is almost impossible to detect in conventional detectors. There are some types of detectors which are called bolometers. They operate at millikelvin temperatures, and they can detect vibrations of crystal lattice in the form of phonons, and this heat can be detected, but it's very sophisticated technique and done in some special experiments. And if you summarize all these three channels, you will get a detection signal, measurable signal. And the task is to measure. There are some other mechanisms, for example, Cherenkov radiation, transition radiation, Bremsstrahlung, but not talking about these three mechanisms. So, now we come to the devices which can detect radiation. There are a lot of types of them, and as you understood from the previous slide, we have to measure two things. The first thing is to measure electrical signal, and the second one is caused by ionization. The second one is to measure light, which is produced due to the excitation. And if we call about ionization, there are several types of detectors. Some of them are called gas field detectors. You can see them ionization chamber, proportional counter, Geiger-Müller counter, and if we are talking not about gases, but about solids, we can have semiconductor detectors. If we are going to detect excitations, we need scintillation detectors. We can detect light produced during the interaction and then particles with the matter. And we also can write one of the most simplest categorization of detectors. We can see and divide by the state of the method, gas field detector, liquid detectors, and solid state detectors. Here's some examples how detectors look like. Use portion counter, use solid state semiconductor detector, high purity ion detector, which I use for gamma ray spectroscopy mostly, and scintillation detector have photomultiplier view. This is a device that detects light and the scintillating material that can produce flashes of light and the particle passes through this material. All these detectors are going to be the topic of my next lectures, today's and tomorrow's. If we talk about detectors, we need to somehow characterize that what we expect from the device to have some basic characteristics of these detectors. And the first, one of the simplest characteristics, which is called efficiency. Efficiency, for example, you have a radioactive source, and you want to detect some, for example, gamma rays, which this source emits. You have a detector, for example, this one, you have a source. Of course, the source basically is an isotropic thing. All gamma rays are emitted in different in four pi angle in different directions, and you have some components to detect for this gamma rays, and the distance between the gamma ray and the detector is like here. And in reality, there are two types of efficiency. The absolute efficiency, which is number of detected events divided by the number of gamma rays emitted by the source. You can get the absolute efficiency. And of course, if we look, the major parts of all gamma rays will be emitted, and you will get only small fraction of gammas. And actually, force efficiency is always less than 100%, less than unity. And the intrinsic efficiency, which is the number of pulses recorded, the number of events which are really detected, and the number of gamma rays which fall on the detector. And this also parameter that takes away this geometric factor and takes into account only the number of events which interact and the number of events which are recorded, because not events, not all gamma rays can be detected. The second parameter and the second characteristic, which is called time resolution, and it intersects with this parameter, which is called dead time. And the main thing of this, in simple words, that you have some events which are recorded, some gamma rays which interact with the detector, but not of them can be processed by your device due to different factors. And if you don't have good time resolution, you will miss a lot of useful symbols. The special resolution is not so important parameter. We talk about conventional detectors, for example, for gamma ray spectroscopy and other applications, because spatial resolution rarely matters in experiments with, for example, high energy physics or cosmic ray physics, where you have to reconstruct the point of interaction particle. Because sometimes it's very important to understand what was the force and what particle lead to this particle, and you have to understand and know the point of interaction of all particles separately. Sometimes it's very important, but as I said, mostly in fundamental applications. And the next parameter, which is called energy resolution, and it's very important for gamma ray spectroscopy. And I like to give you more details about this parameter, this characteristic. I hope that many of you know what is the Gaussian distribution. Yeah, I hope so. Yeah, and this picture, oops, for many of you who are familiar, this is a normal distribution, or let's say Gaussian distribution. In order to quantify the detector, because why this parameter is very important? Because sometimes we have a lot of isotopes, great number of isotopes, up to, for example, 10 isotopes. We have isotopes with a lot of gamma lines. You want to distinguish between these lines in order to characterize your isotope, because all different isotopes have different lines, and in this sense, all isotopes are unique things. You can't have, for example, cobalt isotope, cobalt 6 isotopes with lines except 1.1 or 1.3 MeVs. Can be only cobalt 6, only this isotope. And in order to get this gamma line, you have to get an excellent energy resolution for a detector. Here you can look at this picture. It's just an example showing that you have a good energy resolution. This is this sharp peak and poor energy resolution. This more broader peak. And they actually two Gauss distributions, but with different sigma. And this sigma is very important when we have peaks which are close to each other. For example, 1.1, 1.2 peaks. In some cases, if you have a poor energy resolution, it will be almost impossible to distinguish between these two peaks and to characterize their isotope. And here is more couple of more words about this energy resolution. How to get it? Energy resolution R stands for this. It's just the ratio between sigma and the H0, which is actually the average in this Gauss distribution. That's sigma. But in physics, so detectors, it's important just the rule to use not sigma, but the parameter which is called width at half maximum, which is actually, if you look at this energy distribution, Gaussian distribution, you have the maximum, this point, yeah, and you have half maximum, which is located somewhere here. And if you derive just from the Gaussian distribution, you will get that all times this width as half maximum will be 2.35 sigma. And actually, the energy resolution will be half maximum sigma divided by the average of this bracket. I can now speak this information because I'll come back to my further explanations. And now we get acquainted with all basic detector characteristics and can move to the process, which is called realization. Yesterday, I gave some details about how particles, specifically charged particles, interact with matter. We have the primary ionization, and we have the charged particle that interact with matter, and secondary ionization. And secondary ionization the delta electrons, which have enough energy also to ionize the medium. And here you can see the track, the primary track of the particle, and this the second track which is caused by delta electrons. And the math is very simple. In order to understand and detect your particle, you have to simply calculate the number of electrons which are produced during this interaction. Actually, not only electrons, but also electrons plus ions, which are called together electron-ion pair. And here you can see, for example, here E sub 0, this is the initial energy of the particle which interacted with the material. And here you can see n sub 0, which is E divided by V value, W value. And this W value actually is the average energy in order to create one electron-ion pair. And this actually is an experimental and well-measured parameter. And in order to calculate the number of electrons and ions pairs, you have to just divide the initial energy by this value. And here you can see parameters for different materials, mostly gases. I will give more details in gas field detectors, but again, it's mostly argon. Here you can see W value that is actually measured in electron volts through ion pairs for different materials. And you can see that for argon, for example, this value is about 26 electron volts. What it means that, for example, if you have one inner particle, you simply divide this energy, one Y MV, through 26 EV, and you will get the number of electron-ion pairs. Let's move to the processes which can happen in gases when the interaction and the ionization takes place. For example, that's very simple picture that you have electrons and ions. Actually, of course, when it's ionized, you have some number of electrons, the same number of ions, but not of them they have one tendency. They, in order to measure the signal and collect these electrons in ions, you have to apply voltage in order to divide them. If you don't apply voltage this way, this process happens, which is called recombination. A recombination happens when you have an ion and electron. And actually, they don't want to be separate. They have a tendency to come back, meet again, and form their molecule or atom, initial atom. This is called recombination, and this is a very bad process for radiation detectors because in this case we lose some signal. And to get rid of this recombination, as I said, you have to apply high enough electric field to force electrons escape from this ion. The second process, which is can happen also, which is called charge transfer. For example, we have a positive ion that meets neutral gas molecule or atom, and during these interactions, the change of charges happens. So all these ions and molecules is reversed. One more process which is very bad for radiation detectors, which is called electron attachment. We have electronegative molecule or atom which can attach some electrons. And in this case, electrons are lost. We have a negative ion is actually not can be utilized for our detector. And it's the most important thing for electrons and ions, that's called charge mobility or their motion. In order to detect and measure the energy of each particle in the detector, we need to collect these ions and electrons. And how we do this, we apply an electric field, and under the influence of the electric fields, ions and electrons start moving towards positive or negatively charged electrons. And in this way, we will get a parameter which is called drift velocity. Actually, this is the speed of electrons or ions moving under the influence of the electric field. And this parameter strongly depends on the electric field strength and the parameter which is called mobility. And we talk about gases, pressure of gases, because we have more molecules. We have low velocity. It's inversely proportional to the pressure in the gas. And here you can see just some examples how the drift or the drift velocity of electrons depends on their so-called reduced electric field strength, which is actually the ratio in electric field, and pressure. You can see that the drift and decrease and decrease and decrease, for different substances it behaves in different way. And one more thing, which is very important, that the velocity of ions is much worse than the velocity of electrons, and the difference that electrons are much lighter particles than ions, and these different masses leads to the fact that the electrons move faster in approximately 1,000 times compared to ions. And here we come to the very important plot that's called regions of operation of all gas field detectors. It's based on the notions which I have mentioned in the previous slide, and here you can see the number. Basically, there are different names on these axes, but usually this is voltage next, and current or number of carriers in Y, and here you can see 6 different regions, and all these regions define the operation of different gas detectors. Here you can see the first region, which is called the recombination region, and as I said, this is very bad area for detector operation, because all electrons and ions are combined, and we don't have signals at all. The second region, this is called ionization region, is very important and is used for operating such devices which are called ionization chambers. And I will show you in more details how these detectors work. The third region is called proportional region. In this region works detectors which are called proportional counters. And despite the name, these detectors can measure the energy of the initial particle. And here, just to clarify in these regions, in ionization region, the number you have some finite number of electrons and ions which move under the influence of electric fields, so the electrons, and you simply collect them. In the third region, the proportional region, we have the so-called multiplication factor. Then we apply more voltage to the electrodes, we can achieve so-called gas multiplication. We have more electron ion pairs, and the energy of and the number of these electron ion pairs is still proportional to the initial energy. The fourth region is called region of limited proportionality, and no detectors operate in this region because there are a lot of non-linear effects, and we don't get the energy of the particle. The fifth region is called Geiger-Miller region, and in this area, devices which are called very pretty simple and well-known devices, which are called Geiger-Miller counters, they exactly operate in this region, and the main thing that we have a strong amplification of the initial signal, but can't get the amplitude or the energy of the particle, and only can detect the part of the initial expression. Why this region is called Geiger-Miller region, and detectors, which have the same name, are called counters. But compared to proportional counters, Geiger counters can't measure the energy of the particle. That's the main reason. Because they operate at much greater, more greater voltage applied. And the last one is called just discharge region. If you apply the big voltage to the electrode, you will get a continuous discharge, lots of sparks, and will get no measurable signal. And this really a limit where Geiger region stops, and here no detectors operate. So actually, if we talk about ionization chambers, this is a very simple picture showing this is the detector, just a schematic, and actually the detector itself, it's a capacitor. We have two electrodes. One electrode is called an anode, it's a positively charged. The second one is a cathode, which is negatively charged compared to the anodes. You can have one electrode can be grounded, and the second one should be positively or negatively compared to the first one. And in the presence of electric field, electrons and ions start to and this volume actually is filled with some material. In gas field detectors, basically it's noble gas. We usually use noble gases such as argon, xenon, helium. It's rare, but sometimes it's used. And actually, you have two electrodes and some material beside them. You have actually a capacitor. And this capacitor is characterized by the capacitance. And if you have some resistor connected to this capacitor, you can actually integrate the charge and get the current. Yeah, and you will have actually the ionization chamber. And ionization chambers can operate in two modes, in current mode and in pulse mode. In current mode, you have just electrons and collect all particles over a very long period of time, which is actually represented by this parameter, which is called tau, which is actually the RC, or the R multiplied by C, whereas the resistor, and C the capacitance. And in this case, you will get time, current, you integrate, you will get charge. And I would like to say that in current mode, not a lot of detectors operate, not for so many other applications. For example, for dosimetry, it's used, and I hope that my colleagues will tell you about this in the next lectures. But in particle physics, where you have to measure energy, for particles, we actually use so-called pulse mode. And the difference here, you can see this continuous amount of time, and here you can see in the pulse mode different pulses with different amplitudes, and this value amplitude actually corresponds to the energy of the particle. And when you have a pulse mode, you can characterize all interactions, all particles which interacted separately. Not integrate them, not sum up them, but characterize them separately. And here, just an example, a simple picture how the ionization chamber looks like. Anode. This is so-called the parallel plate geometry. For example, you have an interaction somewhere at this point. It's in red, and when interaction happens, you have a charge pool. And then when interaction happens, you have electrons and ions. Electrons and ions start moving in opposite directions. Electrons move to anode, and ions move to cathode. Yeah, and what we see in our detector, actually we see an induced current, which happens when at the same moment when charges start moving, it starts to feel this this movement by using these capacitance and resistor. And here there's a simple picture showing that how the voltage induced into this charge starts increasing, and here then you see this. It's not clear, I think, for you, but this is T minus and T plus. This T minus stands for electrons, and T minus, T plus stands for ions. Remember, I said that ions and electrons move with different velocity. And in order to fully characterize the particle, you have to collect all charges. You have to collect electrons, you have to collect ions, summarize the current, and you will get the maximum, actually the amplitude of your amplitude of the signal, which is proportional to the energy of initial energy of the particle. But there is one problem, that ions move 1,000 times slower. And if you start waiting for ions, you will waste a lot of time. And there is one trick that you can rely only electrons. You can choose this parameter RC that should lie in the region between T minus and T plus. And you can collect by integrating your charge only in this time window. And in this case, you will collect only electrons. And here you can significantly improve the time resolution and improve the speed of taking these short pulses, because it takes several microseconds from electrons, so it should take electron. But there is one problem with electrons, only relying on electrons when we have dependence on the initial points of interaction. For example, if we work with gamma rays, we have different amplitudes of interaction with it strongly depends on the place in the detector side where interaction took place. That's very important. And the trick is to use this ionization chamber, for example, for alpha spectroscopy or beta spectroscopy, or to add one more mesh grid here. this is called a free-treated ion chamber that allows you to get rid of this dependence on the coordinates of the interaction, but I'm not going to typically this let's just show you that basically ionization chambers collect only electrons. That's the fact that I just wanted to show you, because I think in order to fully explain you how this works, it requires more time and more slides. And we have one problem with the ionization chamber, which is very important if you try to detect low ionizing particles. If you look, for example, for one EV charged particle, typical value of the signal is about 10 to -5 volts. For example, the capacity is usually 100 picofarads, and the signal is pretty feeble, small, and you have to somehow amplify it by using charge-sensitive amplifiers, some electronics, some sophisticated electronics. In some applications, it's not a good idea, and that is why we move to the this region, proportional region. This region is called the proportional region, and the main feature of this region, if we make the electric field inside this capacitor stronger and stronger, we can achieve the so-called region of amplification. How it happens? The electron starts getting some energy from the electric field, from the applied electric field, and this energy is enough to well, let's start from the beginning. You have some interaction which happened, and you have, for example, an electron, plus and ion, and the electron and ion start moving in the direction in the electric field, and this field is strong enough, and electron gets some energy, which is ionization electron, which appeared after their ionization. And it gets enough energy in order to ionize the molecule also. And then it ionizes molecule, it gets some energy from the field, and as the second, you have actually the so-called avalanche. You have, for example, one electron at the very beginning, and you will get at the end of this amplification about 1 million electrons. And this process is called Townsend avalanche, and is also described this exponential expression. Here is the initial number of electron ion pairs, and this is the number of electrons or electron pairs, basically electrons, after the initial electron passes from some distance. And this actually called exponential outreach, it's called gas multiplication factor, and outreach called the first Townsend coefficient, which depends on electric field and pressure. As we talk about gases detectors, we talk about gases, we have all the time keep in mind pressure, because it's very important. It implies the the concentration of molecules. But the main one problem, in order to achieve these electric fields and the electric field strength is about 10 to minus 4 volts per centimeter. It's a pretty huge field, and it only can be achieved in so-called cylindrical geometry. If you apply parallel plate geometry, you will have to significantly increase the electric field, I think up to even 200 volts, kilovolts, and these so high electric field will give you the continuous discharge. But that's why physicists came up with a simple idea to use geometry. And in this geometry, the cathode, the detector looks like a cylinder, and something like this. We have a cylinder, and inside the cylinder we have an anode, very thin anode, which is actually wire, metallic stainless steel wire, for example, with a diameter of 100 micrometers, and a cathode, which is the outer surface of this cylinder, is also metal. The diameter of this tube basically several centimeters, and in this geometry, we can really create a very strong electric field, because electric field strength is governed by this equation. This is applied voltage between anode and cathode. It's the radius, the distance which we measure this electric field, natural logarithm of the ratio of the cathode radius to the anode radius. And in this geometry, you can achieve quite high electric fields in this region, which is called the multiplication region. And this multiplication region is actually very small compared to the whole volume of the detector. It's less than 1% of all value. And exactly in this place, the multiplication happens, and here we can get the avalanche. And this avalanche of electrons start moving like this, and what's called a simulation of this process. You have an initial electrons, and they move, and here in the vicinity of this end of wire, 25 micrometers, this is about 100 micrometers of increase in this region. You can see the increase of electrons. You can get electron avalanche, which is rarely to be seen in the anode. And this electron can give you the same electric signal, which is ionization channel, but the amplitude of this signal in 10 to minus power, 10 to power 5 or 6, and 1 million times more. And in some applications, you don't need additional preamplifiers, for example, to get the signal from the detector, and can detect low energy particles, stray photons, for example, with energies not so high compared to that for other particles. And also, noble gases are used for these detectors, mostly for ionization chambers, or photon counters are used. Noble gases such as xenon or argon, but the most invention with argon because it's much cheaper, and this is the best way. The main difference that this proportional counters require so-called rich gas, which is usually a full atomic gas, for example, CO2 or methane, which is added to the noble gas in order to absorb photons, which can also happen during the phase interactions. Because when particle passes through the noble gas, it actually gives rise not only to ionization, but also to excitation, and this excitation can give you sort of pulses that can mimic real interactions. That's why all everywhere and always all proportional counters are used with a mixture of gases, on the gas, argon plus wedge gas. I think for today it will be the last slide. I will give you some to cover all of the regions, working regions. We covered ionization chambers, proportional counters, and now we're dealing with Geiger counters. And in this region, Geiger counter operates when you apply a very high voltage. You have multiplication factor, for example, 10 to the power of 10. And the main difference between proportional counters and Geiger counters, that's you operate in higher and electric field area, and you can compare Geiger counter to some sort of chain reaction, where you produce electrons from the avalanches, and also you produce excitations with ultraviolet photons, which can also give rise to more and more electrons. And these ultraviolet photons, if you have argon, you always have ultraviolet photons. They create an avalanche, which actually avalanche develops this anode and give you huge signal. And there is, you don't care, you want to have much more ultraviolet photons to support this avalanche. But there is also a problem that if energy, there are also ions which are produced, and these ions also can produce some trigger another avalanches, and this process never stops. And in order to stop this process, you have to quench the Geiger counter, and you have two ways to quench the Geiger counter. The first one is to use external resistor and to reduce the high voltage which is inside, but it's not very good because it's quite slow. We have that long dead time. And the second way is to quench the avalanche by adding also polyatomic structure, which is also called the quench gas, but the function of this gas differs from the gases which are used in proportional counters. There we have CO2 gas. Here we have more complex molecules, for example, alcohol, ethanol, or ethyl. And in this case, these ions, they're neutralized by this by ways of transfer of electrons, and using these gases, you can stop the envelope. I just want to add that actually these quenching gases and these Geiger counters with quenching gases have the limited periods of operating time, because these gases may dissociate and lead to the breakage of this detector. And these detectors are simple. I think they were invented in 1930s and 1920s, and still in some applications we use, for example, in dosimetry, we use Geiger counters, which are one of the best ways to count radiation detectors. I think I can stop for today, and tomorrow proceed with simulation detectors. Thank you for your attention. If you have questions, I can answer them.
Are there any questions?
¿Alguna pregunta en el, lo pueden hacer en el chat?
I can answer them tomorrow.
Thank you very much. There are some things in the chat, but they're in Spanish. It's in the chat. So, you will translate.
Some questions in chat, comments.
So you can. It's not to come. Oh, yeah. Okay. And this also the same. Okay.
Vayan encendiendo sus cámaras, por favor.
Por favor, Ryan, si van a un poco.